Perfect. So here I would like to give you some introduction to high energy physics and how the processes are done. Thanks to Javier for basically the introduction, which we are having also. But here we are in Dubna, Russia, in our institute, where we have the accelerator, which is accelerating particles the same way as LHC, but with lower energies. And we also have some detectors to study processes like quark-gluon plasma and so on. So the event looks like that we have a detector, and in one collision, there are many particles are produced. We are saving them to the trees, or in the future, maybe to these RN tuples. And then later on, we are just moving them to our trigger system. It is filtering the event. Then later on, it's just post-process them. Then reconstruction of the events are done by the detector and software there. And further on, they are doing the calibration. And afterwards, we might see that there are processes that we are saving the files for the physicists. So just to give you a little bit overview, basically in physics, you basically have a model which you have from previous experience. You are trying to simulate on the detector, which doesn't exist at all yet, but then you just go and just model it in some computer. You just process it, do some simulations, and at the end you just get some points from the response of the detector. Then later on you just process the analysis, or you just process the reconstruction, so how it looked like if it would be in the nature, and you are coming back to the same histograms and same distributions. Then you compare the distributions like it would be in nature and how it would be in the model. Then you compare these pictures, and basically if they are same, then you might say that your models are working fine. So most of the time, what we do, we basically at the beginning we have a very big high throughput from the detector to our colder storage. So for that first part, we would like to use some very fast storage. And as one can imagine that DDR RAM is very expensive for that. So we would like to use DAOS for that, just to do that part, filter data, and then do the reconstruction. And when everything is fine, we are just going to save it on colder storages like Lustre or EOS. And later on, what we do, we have the first turn that we go from the raw data via trigger to DAOS and then to Lustre. When the data is ready for the physicists, they are going to read this from this colder storage. They are just reading it, then process it on the huge cluster grid. And then later on, they are also storing it back to the colder storage and then post-process them on their laptops. So let me do this two-way turn and introduce you into that picture. So at the beginning, you have this detector, DAOS, Lustre storage. So let's assume that physicists are going to process their data. So what they do, basically, they are reading from EOS or Lustre storage storages, which are distributed all around the world in the computing farm, which is called grid. So basically what you can see here that we are just submitting many jobs, since events which we are analyzing are independent from each other. We can do it and we can scale it perfectly. So we just submit many jobs. We just process these events, which takes basically hours or sometimes days to post-process them. And later on, we copy these sub-results to the colder storage. And next step, we are just merging these results, like it is shown at the end. And basically, the physicists at the end, they just open the final objects in form of histograms. They open them in their laptops, basically, and then just producing the pictures for publications. So just let me explain what histogram means, what we have in mind. That, for example, let's assume that you have some graph like that you have on the x-axis, you have a time, and then on y-axis, you have some parameter like speed. So this is what you can be like, this is how it goes. This is basically, I was measuring the DAOS system tests. then this is my distribution of the speed. So what we do, basically you have that one, and then to create a histogram out of that, because sometimes you are not interested in time, because you would like to find out that how often you were at the highest speed or whatever, how the speed is distributed. So what you can do, you simply rotate the picture once, second you then mirror it, and then you just let all points fall down to the bin axis, and then you have some distribution, something like that. So this is what you can see. This is the same picture, but we can see that mean value for the speed is 7.4 gigabytes per second. This is how we use histograms. So in our picture, it is like that. So we simply do the same process. So as you can see, the thin line are shown in the grid analysis. So that means that object is small. Basically, when physicists are running the process, then they are just, if their output is in form of 1D histograms, basically they are kilobytes. So there is no problem to merge them and process them at the end in their laptop and just show the results. But since the analysis on the grid takes hours and people would like to analyze the multiple parameters at once, so what they do, they are just increasing dimensionality in the histogram to run process in the grid only once, and then just save as much information as it is possible. But this is what it's happened for two-dimensional histograms. But when you go more and you are trying to do more and more axes, so more it consumes in the memory of the computer at the end. So this is how you can do. Then what you have to start to think that you cannot reserve a memory for whole histograms, because if you have three-dimensional, for example, you have 1,000 bins times 1,000 bins and times 1,000 bins. That means like 8 bytes for a double. So that means that you have already 8 gigabytes of memory. So that's why either you store it in the laptop, or, I mean, you have to open it. You have to be able to open it. So for that, and root has the possibility to do TH and sparse objects, which is not reserving memory at all, but only when the bin is filled or some information is there. But in that case, you have a nice job that you can simply have very big histograms, not fill them fully in the grid. But at the end, you might reach to the point that the objects at the end might be much more bigger than it is on the single job in the grid. So what happens, then you have, whenever you are increasing number of axes, that means that you are worrying that you are not going to fit in memory. So what you do, basically, you just lower the resolution of the histogram or something. But what we would like to do, we would like to go more deeper and deeper. Anyway, you will hit the point. So that's why if you are increasing the size of the histograms, then your output is wrong, or you are not able to open it at all. So for that, there is a DAOS which is here to rescue us when the histogram is in terabyte scale. So what we can do, we can just store it to the, for example, PValue storage, and then we can just have it there. And then later on, multiple user can access and do the projections of different physics. So we have the supercomputer Gavaron in our computing center in Dubna, and where we have the DAOS, which is taken 8 nodes and 32 terabytes, and the next 8 petabytes are coming. So this is what our test we were doing on that one, because what you have to do, first you have to check the implementation, and so this kind of things. So what I would like to mention here, that at the beginning, we have this processing on the grid, but later on we have this presentation layer which DAOS can store for us, and later on it can be used for the physicists. So this is very important part, which is perfectly fitting to our process workflow. So, and at the end, one can see in virtual reality, we have the NDMDR project, which we are working on, that physicists can simply go and click on some bins, and the projections are done that way, that simply when someone will click on the bin, then it is calculated on the cluster, then the query DAOS file system to get the projections, then do some fittings and return back the points. At the end, I will show you the demo. So in our cluster, we tested 2 types of containers, POSIX and key value. So POSIX is very similar to EOS, which we are having at CERN or in Dubna. And we have the root object, which is called tfile, which is basically the file objects, which is stored there. So for POSIX, we use tfile object to store these big histograms there. And we also implemented the DAOS key value object, which is basically using t-message object, where users can save any root objects to the bytes, and then we convert it to the DAOS via DAOS API interface via bytes we store it into the key value. So implementation is there in these, and we have projects. One can look at it if you want. So the ideas are that simply you just create a key value object, you create some histograms, open it, then write it, and close it. For reading, it is very similar. You just use the read function. So we were using DAOS 1.2, and what I was doing, that I was testing that at the same time, from these 8 nodes, we were writing 1 file, 32 files, 64 files, and 128 files at the same time. So just for the test to be bigger, that on one node I was writing multiple files, but I mean at the same time we were writing that many files. And here are the results. So as you can see, the POSIX is a little bit slower when only 1 file at the same time was written. This 100% means that 100% of files were written correctly. So whenever we wrote 32 files at the same time, so almost 4 gigabytes per second. For POSIX, and key value has the 6.5 gigabytes per second. So for 128, we were reaching almost 8 gigabytes per second. But for key values, we were also reaching the speed almost, but we were starting to have some failures in when that key or the object to the current key was not stored. But I think maybe it is because of the version or some bugs there, or maybe there is some configuration in our network. But okay, we can improve that later on. So I would like to summarize that in high energy physics workflow, we can store and read multi-dimensional data structure in terabyte scale in shared address space, create multi-user presentation layer for scientific analysis results. It is 100 times cheaper than DDR, and it will reduce the grid infrastructure usage, and also it will integrate with the colder storage. So here I would like to show you some demo with this 3D view, and then later on Anton can have a presentation on RSC. So we are implementing the project in the GitLab. And so one look at the first link, you can basically do the same thing what I am doing now. And then there's a source, and I would like to thank Technical University in Košice for students who were doing the implementation. So let me load that interface. So here I would like to show you the physics data. So you can move there like you are in Minecraft. So basically the commands are used like for moving. Then later on, when you click on the bin. Oops, okay, sorry. So once more. So, it's a little bit lagging my side. Okay, so when you click, you can see the projection over that bin. Then process is fitted, and physicists can look over different bins. For example, in our case, whenever the color of the fitting function is red, then it means that fitting somehow it's wrong, and physicists can basically with some simple button find out what fits are okay or not. They can adjust it and simply run it again. So as a second demo, I would like to show you, sorry. Okay, like this. Yes. So here I would like to show. Sorry for that. It's not reloading, but I think you get the point, and I will leave the presentation for Anton, and then later on, maybe if you have a question, I can show you more stuff. So thank you very much. Anton, you can take the screen.
Yeah, can you hear me?
Yes.
Yes. Okay. Just a second. Are you seeing this
Yeah,
slide?
we can see the slide.
Yeah, I will be quickly. Thank you, Martin. Hello, everyone. My name is Anton. I'm working for RSC Group. At first, I want to remind that on the previous DUG, we talked about DAOS in the context of our orchestration system called Storage on Demand. And we said that it would be great to use NVMe or Fabric drives instead of directly attached NVMe drives. And first of all, it helps to remove the hardware limitations and also helps to create more flexible configuration of DAOS. And at second, this spring, my colleagues from JINR and RSC built a DAOS with the NVMe Fabric drives using our orchestration system, and we took the 16th place in the RSC 10 node challenge. I want to say the big thank for the DAOS team, for the DAOS community. They helped us a lot with the debug. So the problems we solve with our product, the first of all, it helps to pool underutilized cluster resources and use them more efficiently. Second, it helps to meet the needs of the different users with the different storage requirements. And the third and the last, it allows to quickly and easily isolate resources while we create storage for a specific job or person. Our system consists of two parts. The first one is the cluster management platform that store all information about the available cluster resources, called the basis stack, and the storage on demand part, which is flexible scheduler that manages the storage resources and creates storage systems on user demand. And the last slide, as Martin mentioned, now we have already a lot of storage system in JINR, and now the main goal of RSC is to build an infrastructure for efficient data management. And we are working on it right now, and we'll be happy to demonstrate it at the next DUG. Well, I think that's all. Thank you.